Okay, our lesson today is going to be over what's called the combined gas law. All right, before we get into the combined gas law itself, I want to do a quick review of the three gas laws we've already talked about. All right, the first one that we talked about was called Boyle's law, and it gave us the relationship between pressure and volume. And if you remember, pressure and volume were inversely related, meaning that as pressure goes up, volume goes down, and vice versa. So whatever happens to one of them, the opposite happens to the other. Okay, the second law we talked about was called Charles's law, which was the relationship between volume and temperature. Right, and unlike Boyle's law, volume and temperature were what we called a directly proportional relationship. When one of them went up, the other one had to go up with it, and when one of them went down, the other one went down as well. And then the third gas law that we talked about was called Gay-Lussac's law. Okay, and just like Charles's law, Gay-Lussac's law is what was called a directly proportional relationship as well. When pressure goes up, temperature goes up. When pressure goes down, temperature goes down. Right? So if we look at these three gas laws and look at the equations for them, what you'll notice is that each of these laws only involves two of our three variables, right? The variables that we're talking about are pressure, volume, and temperature. Boyle's law has pressure and volume. Charles's law has volume and temperature. And Gay-Lussac's law has pressure and temperature. Okay? Each one deals with two of them. What that means is we can change two of those things as long as one of them is being held constant, and we can use one of those laws to figure out what happens when we change those values. Okay? But what happens if we want to change all three variables at once? If we have a situation where pressure, volume, and temperature are all changing from beginning to end, none of these gas laws will deal with all three of those variables, right? They each only involve two of them. So when we have situations where all three variables change at once, what we want to do is use the combined gas law. Okay? The combined gas law is basically taking those three equations for Charles, Boyle's, and Gay-Lussac's law and squishing them together to make one larger equation that has all three variables in it. All right, this down here is the equation for the combined gas law. And if you look at it, you can see how it is kind of just all three of them stuck together, right? Boyle's law was P1 times V1 equals P2 times V2. So you have that here on top, P1 times V1 equals P2 times V2. Charles and Gay-Lussac's law was P1 over T1 and V1 over T1 is equal to P2 over T2 or V2 over T2, right? So you have both of those here by putting those T2s on the bottom. So the combined gas law really is just what it sounds like. It's taking all three of them and smushing them together so that we can deal with all three of those variables at once. All right, so make sure you get this combined gas law written down in your notes. You can pause the video if you need to. And then we're going to work through a couple of examples really quick. Okay, in this first example, if we read through the problem, you can see it says initially you have a gas at a pressure of 12 atmospheres. So initially always means that's going to be your P1, V1, or T1 values. And then to decide which is which, you got to look at the units. So this tells you a pressure of 12 atmospheres. So because it says pressure, you know that's going to be P1. So bear with me as I see if I can get this thing to work. Remember our equation. It's P1 times V1 over T1 is equal to P2 times V2 over T2. So if we start plugging things in, we know this 12 atmospheres is going to be our P1. So we're going to start with 12. Okay, we're going to say times. And then it says we have a volume of 23 liters. All right, liters is volume, and it tells us the word volume there. So we know that that is going to be our V1. So that gets plugged in there. And a temperature of 200 Kelvin. All right, because this is given to us in Kelvin, we don't have to do anything with it. We can just leave it as the value they've given us. So our T1 that we plug in there is 200. And we set that equal to our other side. All right, it says on the other side, they're raising the pressure to 14 atmospheres, and they're increasing the temperature to 300 Kelvin, and it wants to know the new volume. So you can see they changed two variables there, which is why we're having to use this combined gas law to find the third, instead of one of the gas laws we already learned about. All right, so our new pressure, our P2, is this 14 atmospheres right here, so that gets plugged in for P2. The temperature is 300 Kelvin, so that's going to be our T2. And V2 is what we're trying to solve for. Okay, once we've got it all plugged in, this works just like Charles's law or Gay-Lussac's law or the mole ratios of stoichiometry. All we've got to do to solve for V2 here is cross multiply. Okay, so we're going to multiply the two things that are diagonal here. So in this case, it's going to end up being 12 times 23 times 300, which, let me pull up a calculator really quick. 12 times 23 times 300 comes out as 82,800. All right, and we're going to say that's equal to our other group all multiplied together. 200 times 14 times V2. So 200 times 14 would be 2,800. Times V2. And then to solve for V2 and get it all by itself, we've got to cancel out that 2,800. So we're going to divide both sides by that value. That's a 0, not a 6. Alright, so we take 82,800 divided by 2,800, and we come up with this value right here, 29.57. And then to find the unit, you just look at what our initial unit for liters was. Initially it was, or for volume. Initially it was liters, so it's going to end up liters as well. So we should have our answer of 29.57 liters. Final answer. Okay, so really this isn't anything new. It's just kind of putting together what we've learned from the last couple days. Alright, let me get rid of all of this junk. And then we'll work on one more example. Okay, our second example here says we have 2.9 liters of gas at a pressure of 5 atmospheres and a temperature of 50 degrees Celsius. So those values there are going to be our starting values, our P1, our V1, and our T1. And then it says, what will be the temperature of the gas if I decrease the volume to 2.4 liters and decrease the pressure to 3 atmospheres? Alright, so let's go back to our little blank canvas here. We're going to write down our equation first of all, just as a reminder. Whoops. Okay, so let's start with P1 times V1 over T1 equals P2 times V2 over T2. And let's start plugging in what we know. We know the initial pressure is 5 atmospheres, so that's going to be our P1. We know our initial volume is 2.9 liters. Okay, and then we know our initial temperature is 50 degrees Celsius. Okay, we can't plug it in as 50 because, like we've talked about before, anytime we're using temperature with gas laws, we've got to convert it to Kelvin before we put it in our equation. So before we plug this in, we're going to do 50 plus 273. That should come out as 323. So that gets plugged in for our T1. And then we can start plugging in our other side of the equation. Okay, we know our new pressure got lowered down to 3 atmospheres. And our volume got lowered down to 2.4 atmospheres. Okay, we also know that the temperature is what we're looking for. So it's going to stay as our variable, T2. Once we've got everything plugged in, all we're doing is we are cross multiplying. So we end up here with 5 times 2.9 times T2. All right, so that should be 14 and a half. Let me make that a dot, not an X. All right, and then on the right side, we have our other pair all together. 3 times 2.4 times 323. I'm not going to do that one in my head. Okay, so this comes out as 2,325.6. And then again, our last step is we've got to get this T2 by itself. So we're going to divide both sides there by 14 and a half. So we'd be taking this value here, divided by 14.5, and that gives us our T2 of 160.39 Kelvin. Okay, because this doesn't ask us for temperature in a specific unit, we can leave it as Kelvin, just the way it is. If we wanted to convert it back to Celsius, we'd have to do the opposite of what we did over here. So instead of adding 273, we would be subtracting 273. So if we wanted to do that, we would just say minus 273, and it would come out as 112, or sorry, negative 0.61 degrees Celsius. Okay, either one of these two answers is fine. It just depends on whether you want to leave it in Kelvin or convert it to Celsius. Okay. So what you guys are going to see for your assignment for today is there's going to be a section of questions that are all about combined gas law. Okay, so it'll be 4 or 5 questions like that. And then there's going to be a section where it doesn't tell you what gas law to use, and you've got to read the problem, figure out what variables it's giving to you, and then based on that, pick a gas law. So if it gives you pressure and volume only, you know you need to use Boyle's law, because that's the law that relates those two quantities, right? If it gives you all three, you got to do combined gas law, and then you get the point, right? So that one, make sure you read the problem and pick the correct equation before you start plugging stuff in. Okay.